So my favorite pastime for going on 11, maybe pushing 12 years now, has been to uh, build little projects with microcontrollers. And I recently added a Raspberry Pi Pico to my collection of microcontrollers. And the cost on that, along with the ease of use on it, is probably going to bring some new people into um, picking that up as something to do because it's really fun to make things happen. So there's lots of tutorials, examples, things like that. So I was taking a different approach on some videos and wanted to just share some little tips, things to consider. So I was going to make a couple videos like that. And if you're just getting into it, you're probably noticing that a lot of the tutorials and instructions and things are just turning on LEDs. This board's not hooked up right now. It was some LEDs I had sitting on top of the pile, so I was like, oh, there's some I can point out in the video. But we're flashing LEDs on and off, which that's what microcontrollers do. It's a digital controller. That means we turn things on and off with it. But you probably want to you may not be one to just do a light show, right? You want to do something a little more interesting than a light show and get from just turning lights on and off up to something more interesting. So that's what I have hooked up down here to the Raspberry Pi Pico board. A selection of motors to get things moving. So if I go ahead and run this, I've got them on cycling differently. But this is how we work movement in. DC motors, which are just going to spin and spin and spin. I think that's spinning a different way than I was pointing. Stepper motors, which we control what part it's turning to relative to. So the next turn is relative to the previous position. Or servos, which are absolute positioning, that where we just say what position we want it to go to and the motor will turn to that position. That's the main ways we get movement in there, and then can do things a little more interesting than flash LEDs on and off. But there are some things to consider. And obviously there are a lot of options on power supplies. So I'll start over here to begin with. Obviously, if it's mobile, you're going to want a battery. Just find the appropriate battery size, probably something lithium ion. This was just on top of the pile, so it was quicker to grab. Just grab the appropriate battery size and plug it up. The Pico may not be your best option for mobility, though, because as far as I've found so far, the chips are only seem to be available on dev boards already. Some other companies, Adafruit, Arduino, they also have the RP2040 available on a dev board, but when I glanced at JLC PCB and PCBWay, they don't seem to have it readily available to stamp on a circuit board to do that, or which means it's going to cost extra for every single circuit board you want it stamped on, and which means you're going to burn up your whole thing, the whole dev board every time for a project with the Pico. So sometimes little chips like some sort of Texas Instrument microcontroller that you can just program and get 20 of them for under $10 might be a better option for mobile things. A little bit cheaper, but still, however you want to do it. It obviously works with the batteries, but 3.3 volts isn't going to run that, so get you an appropriate size battery to handle the motors. Or if it's a stationary project and you just have motors doing things, one excellent option for 5 volts is to grab an old phone charger. So this is an old Samsung. When that Samsung phone died, I just kind of cut the USB cable. So there's an extra one here. But the red and black wires gives us a regulated 5 volts. With other protection things in there. So old phone chargers are a great option to just bring in 5 volts, or if you need a little bit more, the AC power adapters. You've probably seen things like this. They look a little bit different in other countries because of the shape of the plug, but there's still a big box, really heavy from a transformer inside that takes in the local AC signal and sends out so many volts DC. And then I have these cables set up to plug in a breadboard, you might notice. And to do that, I bought a bunch of these. They were from Amazon. The connections. It was a kit for making DuPont cables to go in breadboards, but I just grabbed those end pieces, and they just kind of clamp down any place you need a wire to fit nicely in a breadboard. So cut an old USB cable, and that's in the price range of things to pick up whenever you're a couple dollars short of free shipping on Amazon, sort of thing. Not necessarily anything to rush, put as a high priority, but next time you're a couple dollars short on Amazon, keep that in mind because they're very useful. And then you have all sorts of things to plug into a breadboard, or male and female versions come in one kit. But old phone chargers, most people have those, and these, if you don't have the more powerful AC to DC power supply, they're fairly cheap to pick up. So that's some good options, and then there's lots of options in batteries. You just want to check that and make sure if you're doing something mobile with a battery, make sure you regulate the power going to the board, because that is not going to run off the same power. Like, you would not want to run a Pico off a 9-volt battery. Cut that voltage down a little. So there's a lot of options for power supplies. So in order to make things move, that's the first consideration. The next big thing to consider is regulating the voltage. Basically, microcontrollers, whatever kind we use, these, or I just grabbed two because I only have two hands to hold them, but Arduinos, ESP32s, different Adafruit boards, there's a huge list of them. But these things are, well, for one, we kind of want to protect them because that's the control for whatever device we're putting together. Some of them get kind of expensive. They come in all different price ranges and stuff, but we still want to protect it. So you don't want to go burn up your Pico board if there's a spike of voltage from a motor or something. So instead of turning things on with these GPIO pins, it's always a good idea to use these to turn on another switch. Common thing is a transistor. Here's a 2N2222, very common BJT transistor, where we running power from a collector to an emitter and on the ground. That's part of a circuit. And if we apply or remove voltage to the middle pin, it's like flipping a switch on and off. That can be a much better idea because that adds one layer of protection to between the microcontroller and the devices that could cause spikes or something. There's also Mosfets, which can often handle a little bit more power than the BJT transistors. That's important for motors. This big metal spot on the back is, it's kind of like a heat sink, but really that's more to attach a heat sink to. I guess it does sink some heat as opposed to if it wasn't there. And then you can use the microcontroller to turn these switches on and off, which turn the motors on and off. But an even better idea is to completely isolate it. And that's where we get into things like these over here. So relays, a mechanical switch, there's a coil and some magnetic stuff inside, so that when a small current, like from a microcontroller, is applied, it flips a lever which turns on a switch to control a bigger circuit. And you can have a lot more voltage because they're completely isolated from each other. The 3.3 volts from the Pico can turn on, well, in the case of this one, if it comes through there, either 250 up to 250 volts AC running 10 amps can be turned on and off from that. So kind of big. They don't fit in a breadboard, so that thing I showed a moment ago, that's another use I found for those little DuPont wire kits, is I soldered a bunch of them onto things that didn't fit in the breadboard, like the standard size of relay. That way I can still mock up the designs easily and then solder that in a permanent design after ordering a PCB once everything's finished. Or a nice cheap option for isolating parts of a circuit is an optocoupler, if the lights aren't really going to show up there. Um, this basically has two parts. On one inside this box, there's a small LED over on this side, and on this side, there's a phototransistor. So something similar to this, only instead of applying a current to the base to turn it on, we shine a light on it to turn it on. So this box encloses an LED and a phototransistor. And that way, each part of the circuit is completely isolated from the other through a light wave. So there's no chance of a voltage spike making it back to the microcontroller, and helps to protect that. And again, those are incredibly cheap. It's one of those things that if you're a couple dollars shy of free shipping on your next an Amazon order, pick up 30 or 50 of them for a couple dollars just to get that free shipping and have a whole bunch around. A very useful thing there. So you want to isolate the circuit and do things to protect the microcontroller when you're getting into working with those bigger items like motors that could produce voltage spikes and do more interesting things in the world than just turn LEDs on and off. And one more thing to consider for these. So the last thing to keep in mind is some thinking things, and that's because we're gonna use a microcontroller such as Raspberry Pi Pico to control motors and manipulate things in the real world. We need to keep physics in mind. The physics 101 mechanical sort of stuff. Well, we're moving things around the real world, so we're going to have a change in momentum. And the big one to remember is that the sum of all those changes in momentum is equal to 0. And same thing, we're converting between electrical and mechanical energy, but the sum of all those changes in energy, again, equals 0. So momentum and energy are conserved. Got to remember, that's very important to remember. So change in momentum, just a refresher because that's an important one. So we'll have some mass moving at some velocity, and maybe another mass moving at some other velocity, and we have a bunch of those. And whenever we're changing things, after we make those changes, well, we're just moving things around so our masses don't change. We still have the same masses as we had before, but they're moving at different velocities. So our speeds are going to change, but momentum is conserved. So as we change those speeds, we don't gain or lose anything changing speeds. So that means if we're moving along and try to stop, things don't, when we turn the motor off, the thing's not going to stop instantaneously. We'll have to wait for friction and all that to kind of slow it down. So there's not going to be, that movement isn't as instantaneous as we would, like an LED would be. Which brings us into forces, because another thing to remember with change in momentum is that changing momentum is perhaps a changing force, perhaps a constant force, but a force throughout a time interval. So impulse. So those are the big ones to remember. Where energy is conserved, we get out the equivalent amount of energy we put in. We're just converting it between electrical and mechanical energy, but it is still conserved, as well as momentum. So whenever we change our speed, go to change our speeds of the things we're moving, remember there's still a lot to account for, and impulse, because it doesn't instantaneously happen. It's not suddenly moving and suddenly stopped. That happens spread out over time. So those are the big ones to remember, but well, motors are spinning, so we have torque and different centripetal forces and other things. So make sure you review your physics, but the laws of conservation of energy and momentum are the big ones you want to keep in mind when you start moving things around the physical world. So take a look at the let's take a look at the code running those motors and see how we turn motors on and off rather than LEDs on and off. It's very similar because we're still just turning things on and off, but we have to turn motors on and off in a special way.
I suppose I should have said ways there, because each one of our motors we turn on in a different way. So here's the code for that. So in Python, so just importing the machine and time, like everything for Pico. Then for the DC motor, well, it's just a pin going, just a pin set as an output to turn on and off. And then I don't like to put things to sleep, so I just take a measurement of time and then turn that on and off as if it's been enough time, rather than putting it to sleep. That way the code can continue doing something else instead of just waiting for a certain amount of time. So I try to avoid putting things to sleep. It does show up here in a moment though. And then just a Boolean to keep track of that. So after a certain amount of time, I flip the Boolean, and then if that's true, the pin turns on, and if it's false, the pin turns off. So just flipping it on and off. But I'll put a little picture down here on the screen, and you can see that there's some extra things set up. So that pin turns on and off a transistor. So here's the 2N2222, the same transistor I showed in the scene a moment ago, controlling that separate circuit from the pin that brings in a full 5 volts in this case, as well as a flyback diode. DC motors involve coils of wire which create magnetic fields, and then when that turns on and shuts off, it can create a DC current going the other direction called back EMF. And that's very, very bad for our microcontrollers and stuff. So that diode just prevents the DC from flowing in the opposite direction when the motor shuts down, or kind of gives it a place to dissipate. So some stuff in the circuit, but then for the microcontroller, we just turn it on and off and use that to flip the switch, which in this case is the transistor. Stepper motors are a little bit different. To get that control to turn to the spot that we were from the previous position, we have a series of magnets. It's like 4 magnets on the outside and 4 magnets on the inside, and then we adjust the polarity on those magnets to turn them back and forth. So the pins are going to turn 4 different magnets on and off, and along with that we have a list of the complementary magnets. So there's 4 that will cycle through, and we need to cycle through all of them each time. So like this first one here on pin 13, when it's time for that one, the magnets surrounding it go off or on, and then the other 3 are off. Then the first one's off, the second one's on, and the last 2 are off. Then that second one shuts off, the third one comes on, and that keeps pulling this around in the circle to the spot we want it. And the last one goes off. And then finally, that third one shuts off, and the last one's on to finish pulling that a little bit further around the circle. And then we do that for 4 different electromagnets on the inside. So 4 electromagnets inside, 4 electromagnets outside, and we cycle through them very quickly. So again, just a true or false of whether it's running or not, and that's controlled from how long it's been. However, I'll scroll down here. It was necessary to put it to sleep between each one of those pulses. So like between each of these. So the first one's on, the rest of them are off. First one shuts off, wait a millisecond, the first one shuts off, the rest of the second one comes on, and so on and so forth. I I had it set for a millisecond between each one of those steps, and then a loop going through all those different pins. Hopefully that makes sense there. And then the DC one is just turning on and off, just like an LED, basically. We're just flipping a switch for that one. And then a servo motor, to turn those on, we need a pulse width modulation signal. Very rapidly turning things on and off to simulate an analog signal. Basically, those rapid on and offs average together to give us somewhere that's partway between on, effectively give us something partway between on and off. And servos are fairly straightforward to control. We need a PWM frequency of 50 hertz, so pulsing on and off one entire on-off cycle. We do 50 of those a second, and then we adjust the duty cycle. That's how the percent it's on relative to the percent it's off. So a duty cycle of 5% should be 0 degrees, and a duty cycle of 10% should be 180 degrees, and then we can turn back and forth to the absolute position we want based off that duty cycle running at 50 hertz, 50 times a second, which, if you quickly do the math, comes out to 20 milliseconds. And while I haven't finished thoroughly testing, perhaps it's Python, but running through the main loop on everything I've done in Pico, on Picos, all the tests so far, the passes through the main loop varies. It doesn't take the same amount of time each pass through the loop. It's part of the trade-off for the more speed, but that's varying by as much as 26 milliseconds. And our PWM frequency needs to be running at 50 milliseconds, or 20 milliseconds, so 50 hertz, which is 20 milliseconds, and we're getting 26 milliseconds of variance on the Pico. I haven't done enough testing to really narrow down why that's at. I have a feeling it's in the Python, and that wouldn't show up in C++ or assembly language, but haven't got around to testing it yet. So I did just kind of have to play around with the numbers to find a percentage of the 2 to the 16th, which is 65,536, but we count zeros, so somewhere between 0 and that number, we need 5 to 10% of it. But punching in the calculator of exactly 5% and exactly 10% didn't quite work out because of that discrepancy, which I'm pretty sure comes from the Python, not from the Pico. But I haven't finished testing that yet. But we just turn a 50 hertz PWM signal between 5 and 10% duty cycle, defines what position the servo goes to. So here I just, oh, that was supposed to be unindented there. It's apparently only have it set up to only happen if the stepper motor's going. I'll unindent that real quick. But if it's been long enough, then it just switches back and forth between those two positions I had. If it's in position 1, go to position 2. If it's in position 2, go to position 1. So I was just toggling it back and forth. But the main thing is this up here, how we set that up to run. So each of the motors runs differently, but you can see it's still essentially just turning things on and off, like we see in all the LED examples. So LEDs make nice, easy examples for videos, and we get the concepts that we can then take over to motors in order to manipulate things in the real world. But like I pointed out a moment ago, when you take that next step from LEDs into movement, keep in mind protection of your circuit. Try to isolate the motor from your controller if possible, as well as the laws of physics. Make sure you have those fresh on your mind when you're doing that. But I just wanted to cover all that, and yeah, Raspberry Pi Picos, between the price and ease of use, I have a feeling are going to bring a lot of new people into the fiddling around with microcontrollers. So I wanted to give a few tips on that to help people get started.